with this. It's this equation that I want you to be focused on, right? We're going to work a couple problems with that. All right, we've already kind of done this, but we'll do it. We'll do it again. We looked at these same graphs using just the statement of the Boltzmann distribution, but we didn't look at it using the molecular speeds distribution. So we're going to take a look at the form of the equation and the forms of the graphs and draw some conclusions. We already showed that the Boltzmann, the distribution shifts at higher temperatures, right? And we explained that at higher temperatures we have more energy available in the system, and so we have to populate higher energy states in order to account for that energy. There is another behavior that can be predicted by looking at the m in the argument of the exponent, right? It's in the numerator. And so as the mass of the particle increases, we fall off at a greater rate, which implies that an increased mass of particles, of higher mass, will travel with lower speeds. Yeah? And this is what we expect. The energies of the states are the same, but a heavy particle doesn't need to travel as fast in order to have the same kinetic energy as a light particle that's traveling at a given speed, right? And so as the masses of our particles increase, the average speeds that those particles are traveling with decreases. We've got that v squared multiplier that's sitting outside of the exponent. It multiplies the exponent. That multiplier can be thought to be responsible for the behavior that we saw here at low speeds on the graphs. We said that earlier, it's unlikely, it's very unlikely to find a molecule in a system that's not moving, that doesn't have any energy, right? And you'll see that as v goes to 0, as the velocity goes to 0, that the whole probability distribution goes to 0. So that kind of accounts for that behavior. At lower velocities, we don't expect to have high populations. And so the bulk of the particles will be somewhere here in an intermediate range. We'll have a few at low energy and a few at high energy. So that just itemizes the different multipliers. We already discussed the temperature multiplier. We got the mass multiplier and the v squared multiplier that we account for as well. Okay, so now we're looking for a few things. We want to use our distribution of molecular velocities to calculate those things that I mentioned earlier, the average speed, the average square speed, And we're also gonna be looking at how to use it to get the most probable speed. Did you have a question? Oh, you just had your hand. Sorry, I'll leave you alone. Now that everybody's looking at you, I'll back off. So we want to have mechanisms for calculating these things. I'm going to show you something real quick that, again, this is some StatMech stuff, but at the same time, we do always cover it in this course. It should be fairly simple to get across, hopefully. There's a theory, or I mean, it's just a fact, that if you want to calculate an average value of something, and you've got a system of particles that have a wide range of different values for that thing that you're calculating the average of, one way to go about calculating that average is to take, for each different value of, in our case, velocity, take the magnitude of the velocity and multiply that by the fraction of molecules that have that velocity, and then take the next velocity over, take its value, and multiply it by the fraction of values that have that velocity. Add that to the piece that you calculated before. Take the next velocity, multiply the magnitude of the velocity by the fraction of molecules, and then sum them all up together. And once everything's summed up together, what you're going to have is the average velocity, or the average value for that system. If it's velocity, then it's velocity. If it's v squared, it's v squared. It could be a range of things. But the average values thing tells you that you calculate an average value by multiplying the value by its probability and then summing it across the entire range of possible values, and you will get the average. Let's just illustrate real quickly a case where that is done. So let's say we have 5 balls, and 3 of them are traveling at 3 meters per second, 1 is traveling at 1 meter per second, and 1 is traveling at 5 meters per second. Right? We want to calculate the average velocity that those balls are traveling. And so take the velocity multiplied by the probability. 1/5 of our balls are traveling at 1 meter per second. Multiply 1 by 1. 3/5 of our balls are traveling at 3 meters per second. So we multiply 3/5 by 3. 1/5 of our balls are traveling at 5 meters per second. We multiply 1/5 by 5, and we add all of those together, and we get 3 meters per second. And that's your average velocity. You guys don't know how to calculate averages. You could have just said, okay, well, we have 3 times 3 is 9, plus 5 is 14, plus 1 is 15. I got 15 total meters per second being traveled. I got 5 balls, well, 15 divided by 5 is 3, and my average is 3, right? You could have done that. Or you could have just gone and done the step-by-step mechanism that we used there. The reason I'm showing you this is because this mathematical operation is analogous to a mathematical operation that we can do using the what was that thing called? The Boltzmann distribution of molecular velocities, right? So, look at that for a second. All right. In the previous case, we were looking at just V. You can calculate the average value of V if you wanted. You could also calculate the average value of V squared. And again, you just multiply the probability by the value and sum everything together. What that looks like when going to a calculation is something like this. So this was our distribution of velocities. Remember, there was a V squared multiplier outside of the exponential argument. There was an mv squared in the exponent. So all of this is simply just our Boltzmann distribution. This extra factor of VI is there because we're calculating the average value of V. Remember, this is the probability. Multiply the probability by the value, take the sum across all values, and you have the average. Go ahead.
Those 3.5, I mean, we're talking, it doesn't matter if it's a diatomic, non-ideal gas, and this is a non-ideal diatomic.
We're only dealing with translational motion right now, so we're not looking at vibration or rotation or anything like that. And we'll talk about some of the, yeah, as long as we're just using velocities, it doesn't matter. Okay, so you have your probability, you multiply the probability by the value, you sum across all possible values. Now it's possible that our molecules can be traveling anywhere from 0 meters per second all the way up to an infinite value. So the range on our integration is going to be from 0 to infinity. And just condensing this, condensing all the way to this, multiply the v squared by vi, get v cubed, you have this equation that you need to integrate. Now, to integrate that guy from 0 to infinity, you'll have a number spit out at you, and that number will be the average value of the velocity. Sorry, sometimes I have to stop and remember what order I want to say things. This equation, this integral, can be solved with a table of integrals. So we're gonna direct you in that direction for solving this. We're not going to use the hardcore calculus. I probably couldn't do the hardcore calculus if I was asked to, so that's why we're not going to do it here. But we'll give you tables of integrals, and those tables of integrals will tell you what the integral of v cubed e to the negative mv squared over 2kt is, or mv squared over, or any constant times v squared for that matter. You can plug that in and you can calculate your average value. The other thing that we want to calculate the average value of is v squared. You'll see why in a minute or three why we want to calculate v squared. But to calculate the average value of v squared for a system, just, take the same equation, now we plug in the value of v squared, and so we've got the same integral, except now we've got a factor of v to the 4th sitting right there. And you take the integral of that guy, and you're gonna end up having a value. You'll find the average value of v and average value of v squared are constant as a function of m and t. So if m and t are the same, then v squared will be the same, and simply whatever the answer to this integral is. And that's going to be, it's going to be in your homework, but 2 pages down in notes we're going to tell you the answer. We're just not going to map it out for you. So it'll be your responsibility to take those tables of integrals and integrate those guys and prove that the answer that I tell you is true is true. Oh yeah, and the answers are right here. So accepted value for v squared, the answer to that first, or the answer to this integral is cubed per square root of 3kt over n, and the average value of v is 8kt over pi n to the 1/2 power. All right, so if you're going to execute those integrals in your homework, and you're going to be looking for those answers, your v squared is already going to be 3kt over n. If you take the square root of that, you get v root mean squared, and that's the square root of 3kt over n. And back. How might you find the what do you do when you want to find the most a max value for equation or value? What am I talking about right now? How do you find max values in calculus? So we're going to be looking for the most probable speed next. We looked at average speed. We looked at average square speed. Next thing we want to look at is the most probable speed. What do you do with a function if you want to find its maximum value? Okay. Take the derivative, set it to 0, right? A zero derivative, you've either got the peak of a curve or you've got the trough of a curve, right? We already know that our probability functions don't have troughs, they have peaks. And so if we wanted to find the maximum value for something, what we'd end up doing is taking the derivative of our equation and setting it equal to 0 and finding out where it equals 0 and pinpointing that velocity. If you do that, you will find out that the most probable speed, you're not going to do that. I'm not going to have you guys take the derivative in your homework. I'll just give you the results of it. You take the derivative of that guy, set it equal to 0, and you'll find that the most probable velocity is 2 kt over m to the 1/2. So notice that the kinetic theory doesn't ask much about what the particular nature of the molecule is. It only wants to know what the mass is and what the temperature is. It's not exact. It's not an exact model. We'll talk about what it's not in a moment. Something to note. You look back and take your Boltzmann distribution, you plot your different velocities across the distribution. V most probable is going to be at the top of that hill, right? That's the velocity that you're most likely to find a molecule at. This is the most likely distribution. That's the absolute most likely velocity. Your average velocity will be slightly greater than that. It just means that there's more molecules with energy higher than this than there are with energy lower than this, so the average is slightly greater. And if your root mean square velocity is just slightly greater than that. Okay? Again, 8 over pi times kt over m versus 3 kt over m. So VRMS is just slightly greater than average value of V. Okay, so now we're going to build a little model that relates pressure to velocity. In particular, we're going to relate the pressure to the average square velocity, v squared. And we're going to find something interesting. This is covered in your textbook. It's covered almost exactly the way I'm going to do it. It's not going to be stated the same exact way. The words they use and the words that I use are going to be different, but the math that we're going to do is the same. What we want to do right now is we want to develop an equation that tells us for a system at a particular temperature, with gas molecules traveling at a certain velocity, what is the pressure that these molecules are going to exert on the walls of the container. And to do that, we're going to note that the distribution of gases is uniform inside this thing, and so the pressure on one wall is equal to the pressure on the other, is equal to the pressure on this one, is equal to the pressure on that one. So all of our walls have the same pressure, and we're going to itemize right now just what the pressure is on one of those walls, and that will be, once we run that calculation, we'll know what the pressure is on all of the other walls. Real quick, we can go back to Newtonian mechanics, and we can say that force is mass times acceleration, right? Force is m times dv over dt. Well, that's the same thing, dmv over dt. mv is momentum. And so what that equation is telling us is that the force is equal to the change in momentum with respect to time. So what we're going to be looking for is what is the change in momentum exhibited when one molecule strikes the wall of the container. And then we're going to ask ourselves, in a given amount of time, how many molecules end up striking the wall of that container. And we'll multiply the number of hits by the momentum change per one hit, And the sum of those will be the total momentum change at that, during that time frame for that wall. And so you divide the total momentum change by the total time, and you just calculated dmv over dt, which is the force, and force is, or pressure is force over area, so then you simply divide that by the area of the wall and you'll have the pressure. So that's what we're going to do right now. We're going to figure out momentum change of one particle. We're going to figure out how many particles strike the wall in a given period of time, and then we're going to divide that, multiply those two together and divide by the area. And this gets a little complicated. Again, a lot of these derivations, I'm not going to be asking you to derive them yourselves, but I do want you to kind of understand where the equations that your book gives you come from. So, you've got a particle and it's traveling with some velocity, and it hits the wall of the container. We're going to assume that all of our collisions are elastic and that there's no energy exchange. The energy that a particle starts with before it strikes the container is the same that it has when it leaves. So the molecule doesn't lose its kinetic energy, it keeps its kinetic energy, but when it collides, its direction changes, right? So I don't have this on the slide yet, but it'll be on the next slide. If a particle is moving with momentum mv, mass times velocity, we'll call this v sub x, we'll just assume that we're picking out the x direction, and it hits a wall, and then after striking the wall, it's now heading in the opposite direction with velocity mvx. Then your momentum goes from mvx in one direction to mvx in the other direction for a total delta mv of 2 mvx, right? So in an elastic collision, the total change in momentum for one collision is 2 mv. Keep that in your mind. So each individual collision results in a momentum change of 2 mv. What we want to do now is we want to just take a slice of this box and ask ourselves, how many molecules in that box are, or how many molecules, what's the density of molecules in that box, and what percentage of those will strike the wall of the container in a given time period, delta t. And the answer is essentially that every single molecule inside of a volume equal to the total area of this wall times the distance traveled in that time unit delta t by the molecule. Every molecule inside that volume will end up striking the wall in a given time period delta t. So if I start off with a molecule right here, and this distance is Vx dt, then a particle that's sitting over here traveling in this direction in a time period delta t will be able to make it all the way across this Vx delta t distance and strike the wall. Similarly, a molecule that was just inside of that, given a time period delta t, will have had a chance to strike that wall. And so what we have to do is we have to ask ourselves how many molecules are present inside that volume, and that will tell us how many collisions happen in that time period. And so the number of molecules inside that volume is simply the number density, the total density of molecules in the box, times that the volume of that small little sliver. So we end up with a volume AVX delta T. We'll multiply that volume by the total density of molecules inside the container, and that total density is going to be n times number of moles times Avogadro's number divided by volume, right? It's just number of particles divided by total volume. It's just density of particles in the thing. So we multiply density of particles times the volume of that box, AVX delta T, and then we're going to divide it by 2. Why are we going to divide it by 2? Okay. Because not all molecules are going to be traveling in the positive x direction, right? Of all the molecules that are in this sliver, some will be moving that way, and some will be moving this way. And it's only we're only looking at one wall at a time, and so if we want to ask ourselves how many molecules are hitting that wall, we only need to consider the molecules that are traveling towards that wall, which statistically will be half of them, right? So half of the molecules in this volume are going to result in, they're going to collide with the wall. So our total number of collisions is 1/2 n times Avogadro's number divided by volume times area times Vx delta t. These V's are different V's. If it's got a Vx, we're talking about a velocity in the x direction. If it's just the big V, we're talking about a volume. This equation is here in your book. It tells you, again, what that number of collisions are in a given time period. Anybody want to get me a new computer for my birthday?
Depends. Will I get name points?
Talk to me about that when nobody is here with a recording device.
On camera, it's okay.
Yeah, I'm gonna post this on YouTube. Post myself taking a bribe on YouTube. That's a career move. That sounds like what Leland Yee went after. Did you guys believe that? Democrats selling guns? It's a wild world. Are any of you guys big fans of Mr. Yee? San Francisco natives? No? Sorry, this thing's bogging right now.
I looked on your website, you had some PowerPoints up, and you're not going to be working off those PowerPoints.
Those are the old PowerPoints. I haven't taken anything down yet. You can certainly look at those, but I'll be reshaping a good part of this class this year. Last quarter was my first time doing it. Semester was my first time doing it, and so there'll be a lot of changes. You never do anything the way you want to do it the first time through, unfortunately. So you strike the wall, you head back the other direction, get a change in momentum of 2 mvx, and so the total momentum change is going to be the number of collisions times the delta change in momentum per collision. Multiply those together, and we get a expression. Well, we multiply them together to get the total momentum change, and remember, force is change in momentum divided by change in time. So you divide that thing by delta t. That gets rid of the delta t that was up here. These guys cancel out, and your final expression ends up saying, remember we had a factor of Vx in our number of collisions, and we had a factor of Vx in our change in momentum. It ends up saying that your total force is equal to N times M, the molar mass of the substance, times the area of the wall, times Vx squared divided by volume. Now how do we get rid of that A? Oh yeah, and pressure is force over area. So you take that expression that you got right here, divide it by the area, that gets rid of the A in the numerator, and you have a total pressure exerted on that wall of N times the molar mass of the substance times its x component velocity squared divided by the volume. Right? So that's an equation for the pressure. What we're going to do is we're going to cast it in terms of the average square velocity so that we can get the average pressure. And that average square velocity, that's average Vx, that we said we could connect, or we could calculate